This video demonstrates the use of customized virtual input output and integrated logic analyzer IP blocks for the verification of logic design using Xilinx Vivado tool. For this tutorial, I have considered the design of a full adder. I have already created the project with this part name, that is Arctic 7 is the family, and I am going to use this part name. First create the design source. Next click on create file. Give the file name as full adder. Click on OK. Finish. It asks for the module name and port names. Since it is a full adder, I am going to use A, B and C as the input, sum and carry as the output blocks. Click OK. Double click on it. Let me use the data flow. Assign sum is equal to A XOR B XOR C. Assign carry is equal to A and B or AB, B and C, then A and C. Once the design is completed, save the design. In general, test bench programs are used for the verification of the designs, but I am going to use the virtual input output block and integrated logic analyzer IP blocks to verify this full adder design. For that, click on create the block design, keep the design name or as it is, click on OK. You can see the sources as well as the designs. Now the design source, earlier it has full adder, now it has a block level design added to it, and it has opened the diagrammatic view. Here you can right click to add the model whatever you have created, that is full adder. Click OK. Now the design, this program is present in this design. Similarly, you add IP, which is VIO, virtual input output block. The output of the VIO should be equal to the inputs of the full adder, and the output of the full adder must be equal to the input of the VIO. So for that case, double click on this design. Input to the VIO should be the outputs. So input should be changed to 2 and output must be 3, and they are 1 bit data. Each is a 1 bit input as well as output. Click OK. Make the connections A, B, C and carry with this and this, and add the ILA, which is integrated logic analyzer. Click on this, or you can just right click and click on add IP. Search for ILA. integrated logic analyzer. Double click on it. If you see that these are the inputs and these are the output, totally 5 are there. So you can just use it this as a scope or CRO. So you need to specify the number of probes. So I am going to use 5 probes along with the clock. Check the design, you have the 5 probes. I'm going to use 0, 1, 2 for the inputs. So let me connect this. A connected to the input A, second one connected to the B. This is only to check the output waveform. C, third one connected to C, and the remaining two, 3 and 4, will be connected as sum, and this with the carry. And we have a common clock to be connected. You can just select this design and right click and you can make it as external so that you'll get a clock. Connect the common clocks. The design is completed. Once the design is done, click on validate the design, whether it will have errors or not. So validation is successful. If any missing connections are there, it will give you the error. Click OK. Then regenerate layout. The design has been changed as per the Vivado tool. Now I have to verify this full adder design. So once the design is completed, you can go to the sources tab and right click on this design. Click on HDL wrapper. Click OK so that it will generate a Verilog model of this block design. It is creating the wrapper.v, which is a Verilog model file. And that file will have only one input because no other outputs are there, but we can monitor the inner status by using the ILA because this acts as a CRO. Double click on this to see the view. You have only one input, which is a clock, no other inputs. So once the design wrapper is done, that is generation of Verilog HDL is done, go to the run synthesis directly. We used to have simulation, but directly you can go to the run synthesis. Click OK. Run synthesis will take time to complete the steps. Let me pause and I'll come back. Once the synthesis is done, click on Open Synthesize Design. It shows me the floor plan of this package which I have used. Here we have only one input where you need to define the clock 0. I am using Arctic 7 FPGA development board, which is the edge, and here this is the clock with input N11. You need to define this package so that it can be used as a clock for the simulation. Define the package N11. That is the pin which is used for the clock generation, and IO standard 2 LV CMOS 33. Once this is done, save it by using Ctrl S. Save the design. It asks for constraint file. I'm providing the name as pins full adder. You can specify any name. This is the constraint file which we have provided. You can see this. Here it is. What is the pin? What is the voltage? And what is the clock? Frequency? Everything will be there. Once the assignment of pin is done, you can click on Run Implementation. Click on S. It has the implementing the design here, the full adder module. It also takes time. Let me pause the video. Once the implementation is complete, you can open the implemented design, or next step is generate the bit stream. Click OK to see the implemented design. It gives the statistical report of many factors, power, timing analysis, so many factors it is giving. So straight away you can go to the next step is generate the bit stream of the data. Click OK. It is running to generate the bit stream. In the meantime, you can see the power reports of the device: on chip power, dynamic as well as the static power, power consumed by the clocks, signals, logics, DRAM, IOs. So many information is given. Once the bit stream is generated, just you need to load it into the FPGA or program it. See, this is the design implemented into the FPGA board. So write bit stream is complete. So you can click on Open Hardware Manager. Now it shows that the hardware manager is unconnected. Right now I haven't connected the FPGA board. I'm going to connect it now. Now click on Open Target and click on Auto Connect to detect the FPGA board. It shows that the device is detected here or connected, and but it is not programmed. You can just refresh the device if you want and click on program the device. It will use two files, wrapper files. One is bit file, the second one is debug process file. Just click on program. Now the FPGA is programmed, and observe that we have got two options. One is VIO, virtual input output. The second one is integrated logic analyzer to view the waveforms. So first in the VIO you need to load what are the input and output. So select all of these signals so that they can act as an input and output. You can change this. Right click, the output is a LED, low value is red and high value as a green. Click OK, that is for carry. Similarly, for sum, low value is red and high value I am taking it as blue. This is for sum, and these values can be changed to buttons for toggling the input. Now for 0 0 0 combinations, you have the value as 0 because sum is 0, carry is 0. You can just click on here to see the result. Everything is 0. Everything act as a 0. Now try to change the input 1 0 0 combination. The sum will be 1 and carry will be 0. The same will be replicated in the VIO. Observe the changes. When I provide the input as all three ones, you can see that sum is 1, the carry is also 1. See that in the ILA environment, click here, see that the value is all ones for all three inputs. In this way, you can use the VIO and ILA to verify the functionality of any designs.